Now we're going to shift our focus onto the imaginary numbers. Okay, and for some of you, you might be wondering, why are we talking about imaginary numbers when it's rotations we're considering? But this will become obvious in a few minutes. Okay, so the idea of imaginary numbers was first introduced by this guy here, Cardano, in 1545. But he rejected them in the end as, not real. Okay, he didn't think that they were something that really applied to the world as we know it. Okay, Bombelli, about 30 or so years later, he was the first person who used them and considered that their use was necessary in a way. Okay, so he was trying to solve equations of this form, where you've x cubed equals 3px plus 2q. Now this isn't so important, but it's just that a lot of introductory textbooks usually indicate that imaginary numbers were introduced as a result of quadratic equations, but in fact they were cubic equations, where they came from originally. But even Bombelli, he called the use of these numbers sophistry, and his solution to equations like this were what he referred to as a wild thought. Okay, and even a couple of centuries later, or a century and a half later, Leibniz called these imaginary numbers amphibian. Okay, so there was a lot of skepticism around their origin and their use. Okay, even in this day and age, people have some difficulty with them, but they are a fundamental part of mathematics today, and their use is really varied. You can't get around their use in modern mathematics, and especially in physics. Okay, so briefly I'm going to jump back to an idea we had in a previous video, the group Z2. Okay, the group Z2 is a discrete group with two elements, and the binary operator that I'm going to choose in this case is multiplication. So P and N stand for positive and negative. Okay, so we're going to do positive and negative numbers. So all numbers are either positive or negative, so that they all fit into this this group here. We're going to do the Cayley table. So if you think about it, positive times positive, that gives you positive numbers. Okay, positive number times a negative number gives you a negative number. A negative number times a positive number gives you a negative number. And the crucial thing is that a negative number times a negative number is a positive number. So this is the same structure, same group structure as, for example, a rotation of 180 degrees, okay, or the addition of even and odd numbers. Okay, so these groups are isomorphic, if you remember the terminology from before. So this is this group is Z2. What this demonstrates, though, is that a positive number squared is a positive number, and a negative number squared is also a positive number. Okay, and in spite of Bombelli dealing with cubic equations, we're going to just concentrate on quadratic equations. We're going to take the obvious example, the normal introductory route to imaginary numbers. Okay, imagine if you're asked to solve this equation here. X squared plus 1 equals 0. Okay, well, what you can do is you can bring the 1 over, and you get x squared is minus 1. So what this equation is asking you is, what number, when you square it, gives you a negative number? But we can see from our group here that all positive numbers squared are positive, and all negative numbers squared are positive. So there's no number, when you square it, gives a negative number. And this is why it's such a wild thought. Okay. What these gentlemen did was they suggested that you could let the square root of minus 1 equal to something called I for imaginary. Okay, just let that be the case. Let's see what happens. Okay, well, let's see what happens. What happens is x squared equals minus 1, so x is the square root of minus 1, so x is I. Okay, so our answer is x equal to I. Now this becomes useful when you're solving other equations. For example, x squared plus 4 is 0. Okay, x squared therefore is equal to minus 4. So x is equal to the square root of minus 4, which is the same thing as the square root of minus 1 times the square root of 4, which is 2i. Okay, so you get all other solutions for free. The only extra piece of wild imagination that you have to include is this square root of minus 1. Everything else comes for free.